Okay, we'll go ahead and get started. If you're on Teams, hopefully you see the worksheet and the key that I shared with you. Okay, so number one says find all critical numbers. So we're just going to find the derivative. And if there's a need for common denominators, we'll get that settled. And then we can look in both locations for our critical values. Okay, so H prime. All these terms are set up and ready for power rule. We can jump straight into it. Subtract 1 from the exponent. Bring down 2/3, subtract 1 from the exponents, I get negative 1/3. And then the constant goes away to 0. See what we can do to clean this up. I may have a denominator variable that I have to resolve. And we do need to find common denominators. Okay, so we want to find something. Denominator that both these separate denominators can multiply into. And what's that denominator going to be? 3x to 1/3, right? That's large enough for both these separate terms to multiply into. Okay, so we compare. Let me rewrite this because technically that I want you guys to see that x is with the 10. Okay, so we need to balance each of the fractions, each of the denominators. Looks like this old denominator is missing an x to the 1/3. So I need to balance this numerator by x to the 1/3. So when I multiply these together, what do we get? Just what? Just 10x, right? Because that's the exponent nicely goes away because we add exponents. 1/3 plus 2/3 is 3/3. 3/3 is the same thing as 1. Second fraction, looks like my denominator has not changed. So I can just bring that 2 down with no adjustment. So this is where we want to be so that we can get nice, clean terms to give me one fraction, because now I'm sharing a common denominator. I can push the 2, combine those numerator terms together. Okay. Set 10x minus 2 equal to 0. Set 3x to the 1/3 equal to 0. So those are our critical points, 1/5 and 0. Questions there? Okay, number 2, find the values of absolute extrema. So this is extreme value theorem. And there's one condition, right? It's that fact that we have a polynomial and needs to be continuous on the closed interval. So if I want to find the absolute max and absolute min, we care only about the y values. Okay. And we know that we have some candidates to consider. We have to consider endpoints, and we have to consider critical points. Or we need to test endpoints and critical points. We already have endpoints to test. We'll do that later, but we can go ahead and find our critical points by making our way down to f prime and setting f prime equal to 0. Solve for x. Okay. Do we test every critical point? Do we use every critical point that we come across?
No.
Okay. Right. We go back to our interval, right? We got to remember that we only care about what's inside the interval. If something lands outside the interval, we remove it. It's possible that we do all this work and we realize that none of the critical points are valid, which is okay. What that means is that if that were the case, then we would only test endpoints. So that's very possible, where you go through EVT and you're only testing endpoints because none of your critical points are valid. But in this case, looks like 4 is outside the range, but we can still keep -1. So we have 3 points to test. We have 1 critical point and 2 endpoints. These are the only points that has a chance of being an absolute max value, absolute highest or absolute lowest. So we insert them back into the original function, right? Not into the derivative. We're done with the derivative. Now we're looking for location. We're looking for height, position at these endpoints and critical points. Okay, use your calculators. All right, just inserting it into the original function. -1 into the original function. Three. Okay, so we only care about the y values. The max is 7.5, and the lowest is -48.5. Okay, number 3. Determine if Rolle's theorems can be applied. So Rolle's theorem requires us to determine if our conditions pass. We need to see if function is continuous. Well, looks like we do have a potential issue depending on where that vertical asymptote is. So we're going to set the denominator equal to 0. See if there's any vertical asymptote that could impact our interval. And 15 over 8 ends up being around 1.8, a little bit less than 2, so we're safe, right? There's a break in the graph, but the break in the graph is safely outside of our interval. It's not going to impact our interval, so our function is continuous. And if our function is continuous, 90% of the time, it'll also be differentiable. Right? There's only certain problems, certain types of functions that will be continuous but not differentiable. So we don't have to worry about it here. So, but we do have to make sure we list out our conditions. Continuity with brackets, differentiable with parentheses. No breaks in the graph and a smooth curve, or at least no breaks between the interval and the smooth curve. Next step, find the endpoints, okay? No calculus yet, no derivative yet. We're still gathering information from the original function. Okay, goes into the original function, 3. (24 minus 15 is 9. 9 over 9 is 1. Let's see what f of 5 gives us. (40 minus 15 is 25. 25 over 25 is 1. So that guarantees that these 2 points are level with each other. They both share the same y value. So if you can imagine drawing a line between these 2 points, you're going to get a horizontal line. And a horizontal line has a slope 0. And now we can guarantee that there must be another point on the curve where there's also a slope 0, now that we've confirmed that these 2 points are level with each other. And now we're going to find the derivative, set the derivative equal to 0, and then find the location where the slope 0 is going to occur somewhere along our graph between our 2 endpoints. Okay, f prime requires us to go through Quotient Rule. Okay, f prime g minus f g prime. Go through our cleanup stage here, trying to get all that numerator cleaned up. Okay, so there's our derivative. But we're doing Rolle's theorem. We only care about finding slope 0. So where do we look if we are only concerned about slope 0? Just the numerator. Just the numerator. The denominator will tell us where the slope is undefined, but that's not our purpose, right? We want slope 0. So if we're choosing between numerator and denominator, we're only looking at the denominator. Sorry, numerator. That's the only place where we're going to be able to achieve a slope 0. Okay, we set the numerator of f prime equal to 0. That's right. For Rolle's theorem, it's always the numerator, right? Only the numerator. Okay, I can factor a 2x out. Sorry, I'm running out of room here. X equals 0. And x equals 15 over 4. Now, where do we look to determine which one we can keep? Yep, back to the interval, right? Which one works? 15 over 4, right? That's safely between 3 and 5. And also it's guaranteed, right? We got to find at least one, which we do. But the other one may or may not fall inside the interval, and in this case it doesn't. Okay, so we found the location on the curve where there's a slope 0. All right, good with Rolle's theorem. Mean value theorem, virtually identical. You have a continuity statement, you got a differentiable statement, you're still finding ordered pairs. The only potential difference is that mean value theorem does not require the endpoints to give you the same y value. It could, but it doesn't have to, okay? The points do not have to be level with each other. They can be on a slant, which means that if that's the case, then we have to guarantee a different slope, okay? All right, so this one looks like it's a little bit easier to work with. We know it's a polynomial. Our derivative should be a little bit quicker as well, a little bit less messy, but we still have the same conditions: continuity, differentiability. So again, I want to point something out here. EVT only has continuity, okay? But Rolle's theorem and mean value theorem has the additional responsibility of needing that differentiable statement because it's asking about slope. So we need that. We need that slope condition as well. Okay, just like before, we have to find endpoints. So endpoints gets inserted into the original function. All right, no calculus yet, no derivative yet. We're gathering information just like how we did with the Rolle's theorem. So -1 int for x. -1 minus 1 plus 2, 0. Put 1 in. Zero minus 2 is -2. So we don't have the same y values, which is okay. Mean value theorem, we can still go through. Just have to find the slope now between these two endpoints. Now that we have our slope, we're going to move on to our derivative because we know we're going to set the derivative equal to 0. sorry, not 0. Set the derivative equal to our slope. Sorry. 0 is for Rolle's theorem. We're always setting the derivative equal to the slope that we've gathered for mean value theorem, which may or may not be 0. In this case, it's not 0. Okay, this is where we have to be careful here. I know it feels easier to move that 2 over and then factor with these two terms here. But if you have a quadratic, if you have a square term, a linear term, and a constant, the only way to deal with factoring is you got to get a 0 to show up. Okay, we can't move that 2 over. We got to move the -1 over and get that 0 to show up. And I know it feels easier if you do it that way, but it's not going to get you the right answer. Okay, we got to do it this way. Okay, get that 0 to show up. Now we can factor. Set both parentheses equal to 0. All right, are both of these valid? The 1 isn't. I know it lands at the endpoint, but it's got to be between. Okay? It's got to be on the open interval. So it looks like 1 is close, but it doesn't quite get there. 1 is out. There's only one location guaranteed with mean value theorem, and that is when x equals -1/3, where there's a slope of -1 somewhere along this curve. Okay. Okay, back page. All right, suppose f of 4 equals 12, f prime of 4 equals 0, f double prime of 4 equals -23. Use the second derivative test to state relative extrema. So we're basically going to go through second derivative test to determine what can we say about a relative max or relative min. Is this enough to make a conclusion about relative max, relative min? Okay, so maybe a couple of things that we can do. We can list out exactly what this is telling us, and we can maybe sketch out a graph and convince ourselves what we're looking at. So first step is that f of 4 equals 12. That's obviously just an ordered pair. That's just a point on the graph. We can graph that in a moment. F prime of 4 equals 0. What does that tell us? At this point, at the same point that we're going to plot, slope is going to be 0. All right, so if we think about slope 0, a couple of options, right? Maybe a graph that looks like this, but maybe it's leveling out. Maybe it's relative min. If you look at this, right, these are all slope zeros. So if I just gave you this information, then you would still not really know what's happening, right? Okay, it could be relative max, it could be neither, it could be relative min. It's not enough information, right? We have all these points that could fall into the category. But this third category is going to help us decide what we're looking at, a relative max, a neither, or relative min. So f double prime of 4 is equal to -23. We don't want to get caught up with that number. The only thing we care about this number is the fact that what? That it's negative. That's the only thing that we really care about. This is not a point. I think some students were trying to use this to indicate that's a physical point on the graph. That's not the same thing as saying f of 4 equals 12, right? This is a physical point on the graph. This is representing curvature. And we really are not going to have to worry about how to interpret negative 23 on the graph. We just have to know that it's concave. What? It's part of a concave up or down? Down. Okay. That's the only information that we need to pull from this last piece. And that's what threw off a lot of students on the quiz, just not knowing how to interpret that last piece of information. So if we're talking about concave down, then all of a sudden we have a very distinct option to choose from, right? We know that we must be talking about a graph that looks more like this. So if we're pairing an ordered pair, a slope 0 and concave down, the only conclusion we can make is that the point we're staring at must be a what? A relative maximum. Okay. In this case, we have the ordered pair, which is at 412. Now here, this 7b is also another second derivative test, but this is more straightforward, or this is more, building from the original function. So I want to show this as well, so we can kind of see, two ways of approaching a problem using second derivative test. Everybody good with 7a? Okay. Likewise, if this was giving us a positive number, then we know it's concave up. If it's concave up, then we know it must be a relative minimum, right? So I think a lot of times this number just throws a lot of students off, either thinking it's an ordered pair or misinterpreting it as, a relative min because it's negative. Right. All right, part B. All right, second derivative test, given the original function, we are going to approach it like the first derivative test. We're still going to gather critical points from f prime, but instead of creating a sign line, we're going to insert that f prime critical points into the second derivative and make that conclusion. Okay, so let's find f prime. Set equal to 0. Okay, so normally, right, if I want to find relative max, relative min, your tendency is to go through a first derivative test, which is perfectly fine. I think that is more straightforward than the second derivative test. But if we want to go through second derivative test, we would stop here. Okay, we wouldn't create the sign line, but we ultimately are going to be making a decision between these 2 points. Okay, we know our answer is going to be involving these points. But instead of creating a sign line, we're going to find the second derivative function and involve these points with the second derivative function. Okay, we already know that these are points where slope is 0. Okay, so let me make that clear. We already know these are locations with slope 0. Okay, let's find f double prime. So here's our f prime. F double prime is simply just 2x plus 5. Okay, so we're going to use these slope zeros to help us determine what the curvature is, and then from there make a decision about a relative max, relative min. Okay, so f double prime. Let's test 1 point at a time. So -6 plus 5 is -1. The number is not important. The only thing we care about is that what? that it's negative. And because it's negative, this point must be part of a concave what? Negative is concave up or down?
Down.
Down. So visually draw a concave down to convince yourself. Slope at -3, there's a slope 0 and it's concave down. There must be a relative x. If I want to find the physical order pair, I would insert -3 into the original function, right? I would not use the -1, right? This is not, again, this number is not important. It's the fact that it's less than 0. Okay, likewise, we can do the same test with -2. I get a positive 1. Positive 1, the number is not important. It's the fact that it's greater than 0.
Thank you.
Thank you. This is part of a concave up graph. Therefore, relative what? Min, right? Relative min. Good. Okay, relative min at x equals -2. Okay, so there's two kind of presentations of second derivative test. One is kind of more straightforward, building it from the original function, going through the calculus, and then the other is more conceptual, understanding what that information is giving us. Okay, sketch a labeled graph of the function with the given characteristics. These are all order pairs. I can plot them in a second. I know that my next few statements is referring to a slope sine line. So I can create that. And my last two statements is dealing with a second derivative sine line. Okay, so I'm going to go ahead with this first derivative sine line. This is telling us that slope is negative to the left of -6 and to the right of 2. So that automatically tells us where the critical points are. Negative slope, negative slope. F prime is continuous for all x. If the slope is continuous, what that means is that it's differentiable. That means it's a smooth curve all the way through. F prime is greater than 0 between -6 and 2. That's a positive slope. So we know how the graph is going to flow. It's going to be decreasing to relative min, increasing to relative max at 2, and decrease again. Okay, F double prime, sine line with the last two statements. Second derivative less than 0, that's concave down. Concave down from -2 to 5. And then second derivative greater than 0, that's concave up. To the left of -2 and to the right of 5. Again, I like to create two versions of the graph. I like to create a draft version using just slope sine line, and then I'll retrace it with a more detailed graph. Okay, all these order pairs, I can go ahead and put them down. Okay, so I know how my graph is going to move. It's going to have a relative min at -6. Well, they gave me -6 here, so I know I have a relative max at 2, so I'm going to go towards that relative max at 2, and then it's going to decrease all the way through. Okay, there's my graph. Next up, I want to highlight my points of inflections. There's 2 points of inflection here since they're changing signs at -2 and at 5. Right, they give it to us in this, but if they don't give it to us, then you just plot it wherever it lands on a dotted line. Okay, so now we're going to connect those pieces with the appropriate curvature. We'll go back and retrace, give it that specific curve that we want. So concave up, concave down, and then concave up. Now, when you do concave up, make sure you don't do concave up all the way, right? We got to follow, we don't want to veer off this path. It's going to maintain a negative slope all the way through. So we're only going to show a portion of the concave up. It's only going to be this. Right. If you go any further, if you try to make it curve up, then you're breaking the draft graph you've already created, right? The dotted line is to kind of help you kind of make sure that you stay on track, that you don't veer off track when you do too much of the curve. Okay. Okay, last one here. This is similar to what you saw on the quiz. We want a slope that's negative and concave down. So concave down and negative slope, that's going to look like this, right? So you have 4 options, right? It's either, all the options you can kind of think of as if you were to break a circle into 4 parts, they all have a very specific combination of slope and concavity, right? This will be positive slope, concave down, negative slope, concave down, negative slope, concave up, positive slope, concave up. And we just want to be able to identify the right one. So negative slope, concave down. This is what that graph looks like. All right, see you guys in class.